So welcome back to the online SPICE-SPIN+X seminars series that I lead here together with Libor Schmeckiel, Angela Pittman, and Karin Eversosite now in Duisburg, in collaboration with the SPIN+X Collaborative Research Center that is led in Pastors Latin by Martina Schliemann and Burkhard Hillebrands, and in Mainz here by my dear colleague Matthias Chloe. And then as per usual, this is a Zoom webinar. Please, if you have a questions, write in the Q&A or raise your hands, and I will give you the floor after the speaker is done to ask questions directly to the speaker. And please, again, look at the schedule regularly. We keep updating and having more talks that we're going to be asked all the speakers to join. And if you have suggestions, also send it to us to make an exciting portfolio for this series. So it's my pleasure to my longtime friend Sergio Valenzuela, who is now in ICREA, in the Catalonia Institute of Nanotechnology and Nanoscience and Nanotechnology, CN2 as well. He studied his physics, of course, in Buenos Aires from Argentina, but I know him and we met when he was at a postdoc in Harvard University with Kencam, and was in fact the one that discovered the spin Hall effect in metallic systems, what became very, very important, and it made ubiquitous this physics in many spintronic systems. He works on many aspects of solid state, particularly now in two-dimensional systems with quantum transport, spintronics, thermoelectrics, spin Hall effect, you name it, more or less. He's doing it, beautiful, beautiful, clean experiments that I'm looking forward to hearing more about. He has quite a few prizes, the Cambiaghi Prize, the UIPAP Young Scientist Prize. You know, he's not so young anymore, by the way, but still quite young looking. He has an ESC consolidator, of course, and he's a member of the American, European, and APS fellow. So with this, I'm going to stop sharing and ask you to go ahead and share your presentation and start anytime you wish.
Let me see.
Okay, I only
so
do you presentation? Perfect.
Do you see the presentation?
Perfect.
Okay, perfect. In full screen, right? Well, thank you, Jairo, for this very nice introduction, and also you and the organizers for inviting me to present our work. I think this is a fantastic seminar series, and you're doing a great job for the community to have all of these seminars available immediately to look at any time. So this is great. And today I'm going to talk about spintronics in van der Waals heterostructures. These van der Waals heterostructures are created using two-dimensional materials, and these materials can be exfoliated down to the monolayer. And because of this, when they are put in an heterostructure, they are all interface. And we know that many of the interesting phenomena in spintronics are interface phenomena. And in two-dimensional materials, we have materials that are good for transporting and spin information. We have ferromagnets. We have materials that have large spin-orbit coupling. So we have a spin Hall effect, spin galvanic effects, and so on. We can create magnetic tunnel junctions. So we have a variety of properties that are relevant and are important to look at it perhaps as a model system to investigate spintronic phenomena. Now, one particular effect that we are really interested in is that of proximity effect. If you have a two-dimensional material that is atomically thin, then it can be changed by the environment in which you find this material, and you can actually engineer the band structure. So this talk is going to be about spintronics in general and 2D materials. I will give you a little bit more detailed introduction, but mostly about proximity phenomena. You can have proximity magnetism, proximity spin-orbit coupling, and I will tell you about the ways that we have, together with other groups, develop the means that we have developed to actually investigate these proximity effects. This includes the spin relaxation anisotropy, and the spin relaxation anisotropy tells you if there is a variation of a spin lifetime as a function of the orientation of the spin, and of course, charge to spin interconversion, spin Hall effect and inverse spin galvanic effect. Now, the work that I'm going to tell you have been done, as Jairo said, at ICN2. ICN2 is located just half an hour north of the city of Barcelona. It's an institute of about 200 researchers in a number of topics, many young researchers and a few group leaders. These are the main contributors of the work that I'm going to tell you about, and I'd like to highlight Joseph and Juan, who were working on the recent topics on anisotropy. Thomas and Victor, who are working on spin orbitors in these systems. Also like to mention Frederick and Regina, which former members of the group that work on the topic, our collaborators in Bulgaria, the group of Stefan Roche, who give us theoretical support. So we'll start from the beginning. Why we are interested in two-dimensional materials. So the two-dimensional materials exist in many forms. They can be insulators, metals, semiconductors. For example, graphene is a semi-metal. Hexagonal boron nitride is an insulator. Then you have semiconductors like a transition metal dechalcogenized or phosphorine. But the important thing is that these are probably the most studied materials, but you have thousands of them, and people have been creating databases in which you have thousands of entries of potential 2D materials or likely stable 2D materials. This has been done with artificial intelligence. People have identified potentially hundreds of thousands of materials. But the important thing that I like to highlight here is the creation of artificial materials. You can get only materials from this reduced family and combine the functionalities. And you can do that by exfoliating and stacking or by growing by physical or chemical methods. We do both in our group. The exfoliating and stacking allows you to do devices pretty fast with very high quality. This is something that you need to do eventually if you want to scale up the production of the systems. But the combination of the functionalities allows you to put, for example, transition metal dechalcogenized, which is optically active, is a semiconductor with graphene, which has very high mobilities, with insulators and so on, and have a multifunctional artificial material. Now, these 2D materials could be potentially important for Spintronics. And this is just to give you an example of where people are looking into in their research. The magnetic random access memory, which is a latest application that we can find in the field, it consists of, it's usually represented by the magnetic tunnel junction, which has two ferromagnets and an insulator. These are the two states of the memory. However, this memory is actually much more complicated. If you look at the actual entity, it consists of dozens of layers, one on top of the other, that have each of them a specific purpose, which is represented in this inner circle. Now, if you want to scale this structure, make it smaller and smaller laterally, then you start to have some problems. One of the problems is that it becomes very tall, and that's difficult to handle. And the other problem is that you only have MgO as a tunneling material in the magnetic tunnel junction. You have certain intermixing of the material. There is a roughness inherent in the 3D materials that we use. And this roughness becomes more important when you scale down because you have to reduce the thickness of the barrier so that the resistance does not go up too much. And that's a problem that you could potentially eliminate with 2D materials, for example, because by having atomically smooth interfaces, which are a typical characteristic of these systems, you have layers separated by van der Waals gaps. Now, they can also be relevant to create for tunnel magnetor system. There are some proposals of materials that can replace MgO. You can also create synthetic antiferromagnets or have spin orbitors with symmetries that you don't find easily in the 3D materials. For example, to switch perpendicular magnetic anisotropy. Another property that is relevant is that of voltage control of the magnetization anisotropy, because these are monolayers. They can be monolayers. You can apply a gate voltage and modify the carrier density in the system and then modify the magnetic properties. And then there is the proximity effect that I mentioned before. Now, these are the materials that we use in our group. We use graphene for transport of spin formation. We have two-dimensional ferromagnets. We grow topological insulators of the bismuth telluride family. We also have molybdenum disulfide and this transition metal dechalcogenized that have large spin orbit coupling. These also have large spin orbit coupling, the topological insulators. They're relevant for spin orbit torques and so on. Now, of course, we stack them, we combine them, we see the properties together, but we also combine this material with 3D materials like standard ferromagnetic transition metal ferromagnets like nickel iron or cobalt. And in this situation, you again get the problem that you have in the 3D materials. For example, you can see in this picture from this paper that you have an interfacial layer, an intermix in between the topological insulator and nickel iron. And this is actually very bad. It gives you a region in which you may have not the surface state of the topological insulator or also a dead ferromagnet. They contribute to the torques. So you had to take this into account. It has not been taken into account in the first experiments. And so you need to do some interface engineering for this to improve. And this is an example of that engineering that we did at the beginning a few years back by intercalating, for example, silver or aluminum. And here you can see the spin orbit torque in this system, in particular, by STFMR. The only thing that you have to look at is that the field-like torque is the anti-symmetric component here in red. As you can see, if we change the interface, this is just with permanent BST, you go from something that has this sign to something that has the opposite sign. I don't want to enter into detail, but that changes from some torque that is consistent with the topological surface states here with something that is consistent with Rashba-Edelstein effect, with Rashba splitting down here. And in reality, these topological surface states are not involved in the torque. It's actually this layer that actually conducts. So we found that the interlayer can be improved, going from something very bad, 3 nanometers thick with permalloy, to something that is good, 2 nanometers, to something that is relatively very good, 1 nanometer with aluminum. Now, how can we further improve the interface? And this is kind of things that we are doing now. We can have two-dimensional materials. And the first idea that we tried was to look at all van der Waals heterostructures, and we chose a ferromagnet that has tellurium in it, because we know that the material that goes away from here is actually the chalcogen. The chalcogen is very volatile. It goes to the ferromagnet, and that creates more or less the alloy. We see this by XPS methods. Now, when you do that, you have a material that doesn't want more tellurium. That was the idea. And when we investigated the spin-orbit torques in this situation, we get much larger efficiency and also switching current that are very decent for these systems. Second idea is to use an intercalation material that could be graphene. We chose graphene because we knew that graphene has a very tight lattice and doesn't let any material go through. Even helium can be trapped, and hydrogen can be trapped by graphene. And this was known a few years back. And it was also proposed that if you put graphene here, they can also contribute to the spin torque because of Rashba-Edelstein effect happening in graphene. Well, that was the motivation. We obtained very nice heterostructures. These are done by growing in the MBE, taking it without exposing to air to a globe box, put the CVD graphene, go back to the MBE, grow the ferromagnet. And you can see here that graphene actually protects the topological insulators. This is a region that is protected by graphene. This is a region that is exposed by to the air directly. And by looking at XPS, I will not enter in details, but the XPS actually tells you the chemical properties, the state of the material. You can see there are two cases in the uncovered region for bismuth, 2 peaks, and this indicates oxidation. In the case that is covered, there is no oxidation, and the same happens with tellurium and all of the other peaks. No oxidation, no air with the air exposure. In this case, you can also do ARPES and see the topological surface states in topological insulator, which is very nice. Now, if you do the heterostructure, what you find is that starting, let's say, with bismuth telluride, you have the peaks here. If you put reference materials like just bismuth or just tellurium, the peaks are going to be here. Displaced from the bismuth telluride because here, when you form the compound, there is charge transfer between tellurium and bismuth. Now, if you put permalloy directly on the topological insulator, you see that you obtain bismuth and you obtain tellurium. Permalloy is a very nice material to break the topological insulator bonding. Now, if you put graphene, you still have these two, And if you put graphene and then permalloy, you still have the topological insulator. And when you do the torques in this situation, you investigate the torques, you obtain that you can directly compare in the same film what happens in this structure or in this structure, and you see a factor 25 on the efficiency of the torques for the field-like and a factor 4 for the damping-like. Now, as I said, in this paper, it was mentioned that maybe by proximity effect, you have an additional contribution from graphene, and this might be happening. Actually, we believe it might be happening, but it's very difficult in this structure to actually discern what's going on with graphene. In graphene, this structure have 3 channels that actually contribute to the transport. We don't know how much, to a certain extent, how much current is going through graphene and what is the contribution from the torque from this system or not. Now, the idea is that you have proximity effect, and the proximity effect indicates that if you have a material that is 2-dimensional between other materials, top and bottom, or just bottom, then the properties of that material that you have in pristine state is not the same anymore. So you can modify it in different ways. And this is, in a sense, is a change of paradigm. This is the way I see it. So you have, from one side, the semiconductor industry that looks at material doping, and even in Spintronics in the past, we tried to make, and we succeeded, some people succeeded on making gallium arsenide magnetic by putting manganese, but that led to a lot of problems. You put manganese, you kind of put as much manganese as you want. The manganese start to cluster, you can put a few percent. You also modify the transport properties of gallium arsenide, which can have very high mobility without manganese, and then it drops very fast. Now, if you look at proximity effects, you can modify the properties of the material that you have originally with an insulator, and then introduce different properties into it without modifying the transport properties, the nice properties that you have originally. Now, the proximity effect is very well known in superconductivity, and the reason is because it occurs over distances of the coherence length, which can be hundreds of nanometers. You can have a superconductor, a normal metal, and a superconductor. Everything is superconductor and a lateral device, because you can put electrodes at large distances. Now, this proximity effect that I'm talking about allows you to investigate proximity phenomena very clearly for magnetism or spin-orbit coupling that occurs at much shorter distances, which are typically atomic distances. But because this guy is atomically thin, then you can really modify the valence structure of a whole volume or a whole surface of your system. So if you have graphene, for example, in between transition metal dechalcogenide, which has larger spin-orbit coupling and a ferromagnet below, then a graphene is a nice model system because you can describe it, the Hamiltonian, you can describe it by a Hamiltonian that you had originally in pristine, plus other terms that come from the top and from the bottom. And these are proximity spin-orbit coupling, it can be proximity magnetism. Now, the idea and the purpose of this talk is to discuss how we identify these proximity effects. Well, spin-orbit coupling generates an effective magnetic field in the system, and the magnetic exchange field also generates an effective field that you have in your system. And the influence of these exchange fields and spin-orbit fields, the spin will behave differently. So if you're talking about a spin-orbit field, if the spin is parallel to the field, then it will not precess. But if it's perpendicular to it, it will precess as represented here. So if you are able to grab an ensemble of spins and put them in the proximitized region and see how they behave with different orientations, then you will be able to say something about the orientation and the magnitude of the spin-orbit field. Now, this is going to be the way we are looking into the problem. We're going to look at the dynamics of relaxation and different spin orientation. We're also going to look at spin-to-charge conversion. We are going to focus in the rest of the talk on spin-orbit field. If you want to look at exchange fields and similar processes, I recommend you to look at this paper, looking at spin precession and so on. There are many papers on magnetic proximity effect. Many of them are difficult to interpret and can have alternative explanations. So I will not enter into that discussion. And now, as I said, this is a difficult problem to look at. So we start with something simpler. And I created this matrix of how we did it over time. So we start with, let's say, spin relaxation anisotropy and charge to spin conversion. And we start with high symmetry systems in which we can more or less understand or predict what are the spin orbit fields. And then we go to low symmetry systems in which we don't know at all where the spin orbit field are, because there are no calculations. Difficult to do the DFT in this, and you need huge you need huge cells to do the DFT in these systems because of the lower symmetries overall. So how do we do the spin relaxation and anisotropy? How we investigate this? So we start with a standard Johnson CSV device, which was proposed like 40 years ago, done in aluminum, then again by the group of Van Wees, but in a much smaller volume, so they can observe the effects at room temperature. In this case, it's in graphene. You have a ferromagnet to inject spin polarized electrons in graphene. They diffuse, and then they reach a second ferromagnet. You can see that there's no current circulating here, and this second ferromagnet actually measures the electrochemical potential of the spin accumulation at this point. This is represented in a way here. With one ferromagnet, this one, you inject the spin polarized electrons, you create the difference electrochemical potential for spin up and spin down. The second electrode, ferromagnetic electrode, locks to closer to the electrochemical potential of a spin up for parallel orientation, or the spin down for anti-parallel orientation. You see a difference in voltage here that is all spin related if you make the device correctly. So here you see a representation of what happens if you apply magnetic field along the ferromagnets. The magnetization is typically along the long axis in plane. This is for shape anisotropy. And so a large negative magnetic field, they are parallel, pointing down. And then you reach the coercive field of the first electrode, which is designed to have a lower coercive field. It switches down. Then you continue sweeping the magnetic field. You go from the anti-parallel situation to the parallel again. And then you see this jump. If you were to study this magnitude of the signal as a function of distance between the electrodes, then you will be able to determine the spin relaxation length. But of course, many of you know that it's an easier way to do that with a single device, and is by means of spin precession. And the standard experiment for spin precession is done, represented here. The spins are injected along the ferromagnet. The magnetic field is oriented perpendicular to the plane, and the spins precess as they go from the ferromagnet 1 to the ferromagnet 2. And then you detect the spin projected along this direction. Because you have many spins moving, and this is the diffusing motion, then you have the distribution of angles. And in the end, what you obtain is the oscillation of the signal that dies away for large enough magnetic field where you have 360-degree covered because of the diffusion motion. But we know very well how this behaves. As you can see here, you have that the fitting, which is in red, goes perfectly well with the data, which is underneath in green dots. And from this, you can extract the spin lifetime and the diffusion constant of the spins. Now, as you can see in this standard experiment, the spins are always in plane. So actually what you determine is the spin lifetime in plane. Before, this was not important because the systems were isotropic, but now it's important. Maybe in graphene, the relaxation depends on the spin orientation. So what we did originally was to take the spins out of plane. Very simple experiment in which we apply oblique magnetic field like that, or a magnetic field that is oriented perpendicular to the ferromagnet, and then the precess like this. And the dynamics will actually will depend both on the spin lifetime out of plane and in plane. And this is described in these two papers. This idea was the original idea that we use, but then we found that the magnetization starts to rotate, and is to get this spin lifetime is not very accurate, especially the anisotropy can be small. So in the end, we found that this method is more reliable, but we found that within the precision of our measurements, this is isotropic. Graphene is isotropic, independent of the spin orientation. Now, this actually gives us a nice opportunity. We now have a spin channel, which is graphene, which will not be anisotropic. And then we can look at a region in which we have these spin orbit fields that can induce the anisotropy. So simply, we use graphene as a channel, and in a region in which we intercalated the transition metal decalcogenide. And then see with these experiments, what is the spin lifetime in plane and what is the spin lifetime out of plane by combining all of these experiments here. So we start with a model system in which we have the 2H transition metal dechalcogenized. These systems are rather high symmetry system in a sense. So let me give you some details of the materials that we use. First, we have the honeycomb lattice of graphene, and then you have the band structure of graphene, which has states in the K and K prime point. You have a linear dispersion relation, a description with the mass-like Dirac Hamiltonian. You can have holes and electrons. You can go from one to the other by applying a gate voltage, change the carrier density. This point here is the charge neutrality point. And in graphene, the spin orbit coupling is very weak, and so you can use it as a spin communication system, as I said before. Now we have a transition metal dechalcogenides, and it's been known for a long time that you have large spin orbit coupling in the system. You also have K and states in K and K prime, and but the conduction and valence bands are split. The splitting here is of the order of hundreds of millielectron volts. The splitting here is still of the order of tens millielectron volts, much larger than you have in graphene. And there is an alternating orientation of the spin up to down from one value to the other. And this is simply a consequence of conserving time reversal symmetry. Now, it was also known that if you combine this with graphene, and this was done in the group of Yaroslav Fabian 10 years ago, that you can imprint these properties in graphene. You can have this Vale Seaman splitting, which gives you this Vale spin coupling, so a spin Vale locking, and the splitting and the bands look very similar to those that you find in the transition metal dechalcogenide with a scale that is much smaller, of course, because it's proximitized. Now you also have a Rashba spin orbit coupling that you don't have in the transition metal dechalcogenide, and this is because you put the graphene on top or below a material that has large spin orbit coupling. You break the symmetry out of plane and so on. Now this splitting depends on the material that you use. In the case of tungsten diselenide, it was predicted that you can even have a crossing between the bands because of a spin orbit coupling. And this crossing was observed experimentally. And this shows you that, these effects are not only important for spintronics and the fundamental ideas of spin to charge conversion, anisotropy, and so on, but also for topological physics in which you can generate these crossings by proximity effects. But now here we are interested in determining what is the dynamics when the spin dynamics when graphene is modified. This was theoretically described by the group of Stefan Roche before we did the experiments. I will show you the experiments and then go back how the interpretation matches the prediction done in this paper here. So we'll do these experiments, I said. One important thing that I need to mention is that you have to make sure that there's no conductivity on the transition metal dechalcogenide, or you can control it and investigate it. And because of this, you put additional contacts here, and you can see that there is no transport below a certain threshold. And in order to make things simple here, we just measure below this threshold only. So it's all proximitized. There is no contribution for the transition metal dechalcogenide. Now, our device is also a little bit more complicated in the sense that we have additional ferromagnets, not only this part, which is here, in which we have this in the middle, but we also have reference devices in which we can investigate the transport in just bare graphene. So we have the properties of graphene here, we have the properties of graphene there, and then we have less parameters to investigate what are the properties on the proximitized region. So we investigate, of course, what is the dynamics in graphene, and we can see that if you compare these two experiments, the signal is pretty much the same. This difference is that problem that I mentioned before, that the magnetization actually rotates, but this is very well understood. Now, if you repeat the experiment in this region, these are all experiments. What we found is that if you compare these two experiments, you find something completely different to what I showed you before. The measurements are not the same at all. If you have a perpendicular magnetic field, you obtain a precession signal that looks like the one that I showed you before, indicates some isotropical relaxation in the plane. However, if you take spins out of plane, then the signal increases a lot when the spins are pointing out of plane in this region, which means that the spin lifetime out of plane is much larger than the spin in plane. And this anisotropy ratio, which we define in this way, is much larger than 1. These are measurements that are done at 300 Kelvin. I put it here because I don't want to forget to mention here. It's all room temperature. Now, what it means is that the spins in plane basically have a very difficult time to go through the region that is proximitized by this guy, but the spins out of plane go much more easily. You can create some sort of spin filter. And this paper that I mentioned before from the group Stefan Roche considered 2 situations, one in which you have only intra-valley scattering, momentum scattering. In this case, a spin lifetime out of plane is shorter than in plane. It's only rushed by interaction. But if you induce inter-valley scattering, then isotropy is like what we observed. And this was the prediction here. The inter-valley scattering is much slower. And then due to diaconal relaxation mechanism, the spin lifetime in plane goes down very fast because it sees a fluctuating out of plane magnetic field at each scattering event. And this is something that is very robust in the different transition metal dechalcogenized. It was observed in the Van Wees group in this material. It was observed also in the Nanogune group. In another material, we observe it in the other one that is missing in the family. Now, the other important thing I'd like to mention is now what happens, and these are newer results, when you have a transition metal dechalcogenide, which is anisotropic. And we selected palladium diselenide for 2 reasons. It doesn't share any symmetries with graphene. You see that it's a pentagonal material, and then it also has some rugosity along the A-axis. If you put graphene in combination with this one, you break all of the symmetries. So you could have a component of a spin orbit field in any direction, but you could have a component in the plane. So the situation is going to be very different in this system. If the component is in this direction, you will have that the longest spin lifetime is along this arbitrary axis that I'm selecting. This is the axis that defines the crystalline orientation of the palladium diselenide. If this proximity effect does not need to coincide, and this is defined the orientation by the angle theta. We can define the orientation or determine the orientation of a crystal in different devices by doing Raman. It's very anisotropic for Raman, this material. The A-axis in this device is oriented here. In this device, it's oriented there. You can see it from the symmetry of the Raman. Now, the experiments. How do we determine the spin orbit fields here? It's a little bit more complicated. We had to make the spin process in different ways. But we again have a reference device to determine what are the properties on the graphene channel alone. And then you inject the spins and you investigate with a perpendicular magnetic field what happens in this part. Forget about the palladium diselenide now. If you apply a perpendicular magnetic field, it doesn't matter if the spins process in this way or that way. It should give you the same result because these 2 ferromagnets are parallel to each other. And this is what happens. They're parallel, and then you obtain a perfectly symmetric system. You obtain the diffusion constant and the spin lifetime in this region. Now, you can also apply a magnetic field along the injection direction. And in this situation, you have that the magnetic field is parallel to the spin. There is no torque in the spins. There is no precession. As a function of magnetic field, you find that is a constant. Now, the question is that, okay, this is something that we knew, right? Graphene is isotropic in plane. This is due to the symmetry of the material, and that's it. Now, what happens if we have the proximitized region with this material? Now, let me go back so that you are not distracted. If you have a spin orbit field in this arbitrary direction, I mean, we apply a magnetic field that is positive, the spins will precess like this, let's say, and then it will come more perpendicular to the spin orbit field. And they will be affected more, they will relax faster. If they apply a negative magnetic field, then it will become more parallel to the spin orbit field, it will relax slower, in a slower manner. So in this situation, you can expect an anisotropic response. And this is what we see. And we can actually fit this response by considering this angle which is not 0, it's 70 degrees in this case. And we can also identify what is the longest spin lifetime along this spin orbit field in the plane and the shortest spin lifetime perpendicular to it. And this is a fitting. And these are the only parameters that we use here, because the other ones are determined with the reference device. Now, we can do the same in this situation again. I will not show you this to not spoil it. You have a magnetic field oriented along the ferromagnet. Of course, when you inject the spins, they will not precess. However, when the spins reach this region, they will be dephased because of the spin orbit fields that you have there. They will come more parallel to the spin orbit field in a sense. Because the magnetic field is no longer parallel to the spins in this region, these spins start precessing and gives you an additional component for dephasing because they go back to where they don't want to be. They precess, they go perpendicular again to the spin orbit field. And because of that, you get a decrease on the spin signal, as you can see here. And the only fitting parameter in this line that you see blue is the spin lifetime perpendicular to the plane because the spins start to precess out of plane. And these are the same that you get here. So with this, you can see that it's highly anisotropic. I really like this measurement because it's like a smoking gun. You don't expect to see anything if it is not anisotropic. And then X prime and Y prime, the axis here, which is maximum spin lifetime and minimum spin lifetime, do not align to A and B. This is a strong indication that it's proximity effect. You can continue doing these kind of experiments and actually fine-tune the spin lifetime in different orientations. For example, by applying magnetic field in this direction, we can use the same parameters and look at all of the little details for the magnetization aligned with the magnetic field here or with the spin precession. Parameters are all the same. We can look at the spin signal with oblique spin precession at different angles, and the fitting is actually quite good. Interesting result also is that these results are tunable. So you can change the carrier density by applying a backgate voltage. Here you can see it. And then the anisotropy actually changes. And the anisotropy in this case goes smaller and smaller if you go towards the right here with positive voltage when you have more electrons. And the anisotropy goes from something that is 12 factor, more than a factor 10, to something that it goes 2.5, but it's still significant. And you can see that there is a drop on the spin lifetime in the X prime direction. The other ones more or less stay constant. And you can see here in these values. So this indicates in all situations that the spin lifetime in this direction, which is where the spin lifetime is longest in the plane, is much larger than the other two, which are very similar. This is an indication that for whatever reason, the spin orbit field is along X prime in this device. And I wanted to mention some calculation in another system. There's no really reason why it shows the same result. This is graphene and tin telluride, again, by the group of Yaroslav Avian. And they use tin telluride, which is also highly anisotropic here. In this case, it's square, not pentagonal. And they also observe the same hierarchy. And this is a situation that does not repeat in other systems, but I just wanted to show you that, I don't know, they also obtain the same kind of anisotropies and the spin lifetime in the plane. And so we need to investigate. We don't know. In this situation, there is DFT done. In our case, it was not done. And the experiments were done before the theory that appeared. Now, the other thing that I will talk about a little bit faster is about charge to spin interconversion. They also give you information about the spin orbit field. Of course, you have a spin Hall effect, which is very well known. It was mentioned by Jairo, is analogous to the Hall effect. In the Hall effect, you get charge accumulation in the presence of the edges, in the presence of external magnetic field. Here you get, in the presence of spin orbit interaction, when you apply a charge current, you get spin accumulation at the edges. Now, you also can have inverse spin galvanic effect when you have helical states like shown here. If you apply a current, let's say, towards charge, an electron current towards the Y direction, you populate more these states, and you populate these ones, and then you create a spin density. These are the two main effects that you can have. In the past, we investigated the spin Hall effect in this kind of structure. You inject the spin polarized electrons from here, and you measure the voltage in a kind of Hall cross by the inverse spin Hall effect, or you apply a charge current here, and you measure the spin signal here. You can also look at the work of Totani, which were done, I think, simultaneously to our work here, but with platinum in this sense. Now, in transition metal decolcogenized graphene, we knew that you could have a spin Hall effect, and this is the work of a group of Stefan Roche, or you can have inverse spin galvanic effect or Ralph-Edelston effect, and this is the work of the group of Ferreira and York. Now, we thought that we could use, again, the spin precession in a way to try to determine what are the contribution of these two. And for that, we wanted to first study a system in which we can demonstrate spin Hall effect in a known structure like platinum in graphene by using a spin precession. We apply a perpendicular magnetic field and see the response. And you can see that for a spin Hall effect to be detected, it has to be in this direction. The spins they are generated in this way, but the spin polarization of the electrons is in this way. So you have to make this a spin process. So that's why we apply the perpendicular magnetic field, and we obtain this antisymmetric curve. These days, people describe this as antisymmetric Hanley. So now we use this idea to use precession to determine spin Hall effect in the symmetric system. With this one, the tungsten disulfide again. So a spin Hall effect generates in this structure spins that are out of plane, as shown here, and the spin galvanic or inverse spin galvanic effect generate by proximity spins that are oriented in plane. None of them contribute to the signal as zero magnetic field if they are perpendicular to the ferromagnet magnetization. However, if you apply magnetic field, let's say along this blue electrode perpendicular to the red ones, in this case, you make the spins that are due to spin Hall effect precess, and then you detect the signal. Now, if you apply a magnetic field that is perpendicular to the plane, these guys do not precess, but this one precesses, and then basically you can detect the inverse spin galvanic effect. That was the concept. This is described here. There are other papers in which they look at, for example, spin Hall effect in the nanogune work using nanogune team using a spin precession. There are also spin galvanic effects, topological insulators, or transition metal decolcogenides in these works in the Sarosh-Das group. There are other works in which they rotate the magnetization here to detect the spin galvanic effect, but there should be some caution on interpretation of the result. You have to do it very well because you can have other artifacts, especially in graphene, when you rotate the magnetization. There could be stray fields and so on. So better to look at spin precession. Again, we look at regions in which there is no transport in the transition metal decalcogenide. We have a device that is much more complex that I showed you in the previous slide with many electrodes to actually characterize the graphene and characterize the transition metal decalcogenide here and the region underneath graphene. And what we find is that below this threshold that I told you, we have the charge neutrality point, which is very nice because we can investigate a spin to charge conversion as a function of electron or charge of Hall carriers. So first, you determine the properties of this region, spin lifetimes in this region too. These are all the parameters that you need in order to then interpret what happens with the spin Hall effect. The spin Hall effect, you apply magnetic field along this direction, so that this spin precess. As you can see, the signal is zero. Okay, there's the background here that is removed, but it's the coincides for the orientation in this direction and the opposite of the magnetization. And then when you take the difference, you obtain this signal here, the dots. So this perfectly reminds you of this one. So you really see it from the raw data. You don't need to take a difference of two different curves that give you something. And then you only have one fitting parameter, which is this line in here, which is the spin Hall angle, because the other parameters you know. And now the spin Hall angle is tiny, as you can see, 0.3%, much smaller than a few percent that, or 10% that you can get in platinum. However, the reason why you actually can detect this signal is because the spin relaxation length is longer. What matters is the product of these two, which is larger than what you see in platinum. And what it means is that if you have, let's say, in the inverse spin Hall effect, you have a spin current, the spin current propagates over the whole length of this part that is proximitized, and and the spin current contributes to the spin Hall inverse spin Hall effect signal along the whole width. If you had a much narrower, much shorter spin relaxation length, you will have a shunting that would be much more important, and then you would not see it. Same effect same experiment you can do with the spin galvanic effect, but now with a perpendicular magnetic field, again, you get an efficient which is rather low, but it's still sufficient to see it because of the long spin relaxation length. Now, what I said is that you can actually control the density of carriers. This is the charge neutrality point, the resistance of graphene underneath the topological insulator, the transition metal dechalcogenide. And then you can see that the spin Hall effect, and this is, I don't know if I said, but this is all room temperature again. You can see that you find a peak and a strong variation of a spin Hall effect. For the spin galvanic effect, which is in blue, you see a change in sign, which is expected because you go from electrons to holes. Now, what happens when you have a low symmetry system? And in this case, we picked a tungstenite telluride. And in this situation, you have two symmetry planes. This symmetry plane is a mirror plane that requires a glide, which is represented here. And because of this, is actually a symmetry that you have in the bulk. So it doesn't matter for something that is very thin. So this symmetry does not exist in a device. And then you have this other mirror symmetry, which is broken if you have an arbitrary angle between this material and graphene. So in general, no symmetry planes in tungstenite telluride graphene, and that implies that you can have any components for a spin Hall effect. If you have two planes of symmetry, then you have this right-hand rule in which the spin and the spin current and the charge current and the spin are perpendicular to each other. If you remove one of these planes, then you can have these two components. If you remove all of the planes, then you can have any random components. So how do we determine, and this is the orientation of the spins in this system? Well, the idea is kind of simple. The same happens with the spin galvanic effect. So we need to at least determine what is a spin Hall effect and what is inverse spin galvanic effect. The trick is simple. In the inverse spin galvanic effect, you generate spin density. So it's the same from propagation point, you measure the same this side and this side. And the spin Hall effect, you generate a spin current. So you expect spin accumulation that is opposite on this side and that side. So you measure on both sides. That's what you do. And in this situation, you will see something different here and here. It is the same, then it's only a spin galvanic effect. It is different, is this guy, it's opposite sign, it's this guy. If you have something intermediate, it's both. And we have both, right? It's not opposite sign and it's not the same. It is the same if you make a spin precess in a different direction, but by making the precession on different orientations, we can actually disentangle the orientation of spins here and determine what is a spin Hall effect and what is not. So now I told you that we can also determine the strength, and these are the last couple of slides. How do we do it? Well, we said that there is a spin precession, and the relaxation and spin to charge conversion can give you something different depending on the strength. The first one that I want to show you is that we can determine the strength by looking at the spin Hall effect. You can see this gate dependence, and yeah, one more minute. And then you see that it's asymmetric. And this asymmetry, we thought that it could be related with the numerical simulation that you already have a few years back. In this was done at very low temperature, and you actually had a change in sign. And the change in sign, because it is done at room temperature, can be actually smear out. And that was the hypothesis. So we studied as a function of temperature. And when you do change in temperature, you're basically comparing the strength of spin orbit fields with the energy associated to the temperature. And then you can tune in the spin orbit fields and find when you find a match. And simply using the same signs and values and multiply by a factor 2, we obtain a very, very good match and a change in sign that you would expect. So spin Valley Siemens is of the order of 2 milli-electron volts. Now, in regards to the Rashba spin orbit coupling, it was done by the group of Iris Ferreira who analyzed our data. These peaks here are associated to the Rashba spin orbit field, which does not influence the spin Hall effect. And what they did is to demonstrate that this is actually 20 of the order of 30 milli-electron volts, which is much larger than what you would expect. And this is something that we don't understand yet, but is consistent with other experiments that have been done with quantum Hall effect and so on. And the very last slide is regarding graphene and palladium diselenide. Anisotropy can also help you to determine the spin orbit fields. And it can be described by diagonal relaxation in the valley and intra-valley. And now we know that in this material, you have the spin orbit coupling along X prime. So the other components are 0. And then by using simply that assumption, you get the anisotropy. And by using particular values that you find in graphene or similar heterostructures, you can find a spin orbit field that we have persistent along X prime. So we've done this. I only mentioned that we are also looking at complicated systems, and stay tuned that we can actually look at proximity effects in systems that are all conducting, graphene and FGT, for example. And with this, I just want to conclude. We have I have discussed the importance that 2D materials can have for Spintronics, and this is based on the fact that we have a huge variety of 2D materials, and also because they can be stacked one on top of the other and make very thin structures and probably help on the scaling of this system. Of course, the problem that no one talk about 2D materials, you can have a deck of cards, but then they don't interact between each other, and then they can be spread all over the place, right? But this is beyond the point of this talk. So I show you the relaxation and anisotropy, 2 cases in which you have this hierarchy of relaxations, and then also the spin relaxation and anisotropy. And with these 2 measurements, we can get information on spin lifetimes, and we get information of a spin orbit coupling. And this allows you to start understanding how to get anisotropy in different systems. We are actually putting other materials, and we know a little bit what's going to happen. And so you can tune the spin orbit for your purpose, or for some topological phases and so on. So with this, I just want to conclude. 50 minutes, good. Thank you.
Thank you very much. So that was a wonderful talk, and it's always